Thank you everyone for joining today. And we are starting with our second section. See, this is in continuation to our AWS syllabus. The reason we are talking about Docker and the architecture and also the components around Docker is to get familiar with how Docker works, because in almost the entire cloud environment, not just limited to AWS, even in Azure, GCP, Docker as well as the container plays a very major role in the cloud platform. So having a very good understanding about container, especially on a proven platform like Docker, it's essential. So we are going to discuss about ECS, ECR after a couple of weeks. But before that, we are trying to understand the basics about how Docker works. And there are lot of misunderstanding about how Docker works. Some of us think like it is an alternative for virtualization concept. So it is not the case. So virtualization is a parallel concept. Containerization is different. We will get to understand the difference between virtualization and containerization. And also, some of us have a doubt whether Kubernetes is a replacement of Docker, or how Kubernetes is kind of augmenting the capabilities of Docker is something we need to understand, because some of us think like Kubernetes has killed Docker, and Docker is not at all in use currently. That's a wrong understanding. It's a myth. I will clear what happened for Docker, and what is the current status of Docker in the market, and why we should really understand, even in the current AI era, why we should continue to learn Docker. Okay, I'll make that clear today. And also we'll try and touch base on the architecture, and we will try and do the installation and so on. And later, yeah, we will get into the deep dive aspects of how to create an image, how to run the containers, manage them, networking, and then how to deploy multi-container application. So all those things we are going to discuss later, and also how to secure, and then how to store the images in a private registry. So all those stuffs will be discussed before we get into the Elastic Container Service and Elastic Container Registry topic. Okay, with that, I will start with the container fundamentals, and I will also share the GitHub link to you all. Okay, so I've created a GitHub link for this specific session. I will just show you that quickly. Maybe Docker. Just show that, open it here. So you can follow along the details from the GitHub as well. So you can start with the README, where you can understand what is Docker and some of the key concepts behind. And you will also get to understand the history and the evolution of Docker. See, I'm not going to spend too much time about history and evolution. I've shared a video yesterday about the evolution of Docker, how it started. And see, some of us have an understanding that container concept only started 10 years or 12 years back. It's not that. So containerization concept was there even before the Linux containers, and I have explained the history behind it. Okay, so you can go through that later if you're interested. And so this is where we are starting here. We'll get to understand from the basics of container. So the detailed documentation is available in the GitHub. I'll share the link. It's open for everyone. And you will also understand the Docker architecture and so on. So every single topic that we are discussing for the next 3 weeks around Docker and container, and including ECS, ECR, you can access it from the GitHub repo link that I'm going to share with you all. Okay, so let's get into the container introduction. Okay, so yeah. Okay, so before in fact getting into the container, we'll just have a quick briefing about virtualization and containerization. See, I've already clarified with the detailed 25 different points in one of my session, but you can watch that later. But at a very high level, I'll give you understanding of how these two technologies are different, and how these two technologies complement each other, right? So before containerization, there used to be a lot of challenges when, and especially in the software development side. So people used to develop application, and they focus only on the application code. not the entire dependency or libraries and also the associated runtime stack. See, maybe the developer might be using different operating system. They might be using different runtime stack. But when we run it on a different machine or a different server in the production environment, most of the times it doesn't work because the OS version might be different, or the compatibility issues might be there. The software stack, the runtime environment, maybe they might have used a different Python runtime environment or a Java runtime environment, but then in the production or UAT, you might be having a different, complete different runtime version. Okay, it's not the complete product as such, but then we might be using a different OS version, we might be using different patch, different libraries, and even if there is a mismatch in the libraries also, the application will not work. It will say the library is missing, or the DLL is missing, and so on. So this was the problem earlier before containerization came in. And with containerization, actually what was done is, the developers started creating the application, not only focusing on the application code, but also they started putting all the necessary dependencies, the packages, the backend runtime environment. So all those things are bundled together into a package, into a folder, into a container. So that's what we are seeing it on the Docker platform. So mostly the container that we are seeing, it's not just about the application code. It has all the necessary associated dependencies and libraries where you can use that folder, or you can use that package to run the same exact application on your local desktop, in the server, in the cloud, anywhere, right? So it is going to be giving you the same exact result irrespective of the system you are running. And it doesn't have a separate guest OS as such. So it quickly boots because it leverages the underlying operating system. See, I will just give you a little bit briefing and then I'll come back to the same slide. See, generally, you have the physical server and the host operating system. See, the operating system has two major elements. One is the kernel. See, kernel, as you already know, kernel is mainly for the applications or the utilities to access the physical hardware. So whether it needs some graphics card usage, or memory, or CPU, or network card. So the kernel helps the application and the utility to access the physical hardware, right? And then you have the other supporting utilities, dependency files, and other libraries, and so on. So that is the second part. It is needed for the application to perform its functionality, right? So for application to work, it needs a minimal hardware in terms of CPU, memory, graphics, and so on. So that is provided by the kernel. So the kernel is the common OS kernel, is going to be common across all the different applications. So that is what is shared in container engine. It's not the complete entire OS. The OS kernel is shared, and then what the developers have started doing is, they have started putting all the packages, all the libraries, dependencies, and the runtime stack into the container package itself. So it doesn't have any kind of dependency on the underlying host operating system. So the host operating system has two layers. One is your kernel and some of the other dependencies. So but in reality, the containers doesn't go and check for the libraries or dependencies on the OS itself. Instead, it will have inside the package, inside the container itself. So there is no separate guest OS to boot. So underlying host OS is the common platform, and you can add as many containers as you need, and you can move them to different hardware, different platform, from on premises to cloud, or one cloud platform to another cloud platform. It is very easy because it's just a folder, it's just a package, it's just a container zip file. Okay, you can port it, you can move it anywhere, and the image can be run as a container in any location. And also you have a very good isolation. Docker also has some security products like Scout and other things where you can enhance the security. And by default also, like, you have option to segregate the file system network, and you can have the resource limits and all those things. So some of these features are already available in virtualization also, in your VMware ESXi, or VMware vSphere, or your Microsoft Hyper-V, and so on. But there are certain additional features and functionalities that are available in containers. Okay, so why the term container? So as you could see from the image, see, if you don't have something called container, right? Like this. So the idea came from here. Okay, so that's the reason I'm using this image. So when Docker and the container platform was developed and named, so the name, the terminology came from the shipping industry. Okay, so if you think like without the container for each of the different goods that we are sending, what we have to do, we have to put every single thing into the ship directly, and you cannot have too much of load sent into it. So if, see, for example, if you also move the let's say the truck or the car from the ship, so there are quite a lot of difficulties. So there will be damage, there will be difficulties to load and unload. So but then in containerized platform in the ship, so it is easy to dock it, where you can easily port it from one ship to another ship, or you can take it away from the ship with easy way of loading and unloading. And also it is protected, right? And also, see, for example, if there is a kind of high wave or some kind of natural disaster, a lot of security issues are there. Things might fall off, there might be damage and other things, right? So shipping industry came up with a kind of idea on how to send some of the goods. See, you cannot mix also here, right? See, food and other automobile parts cannot be put into the same thing, right? It will have different effects. So some of the vegetables, fruits has to be put into a different freezing condition or something different, and whereas the other has to get different treatment. So if you put all of them together, then there is a kind of lot of problems come. Okay, so here in the computer, in the Docker, in the application world, see, putting all the application directly into your operating system, it creates quite a lot of confusion, right? Because like there are conflicts, there are driver issues, library issues, dependency issues. One application might need different version of library file, one another application might need another version of OS level patch. So there's quite a lot of problem on the computer application industry also. So that's how they came up with an idea on how shipping industry takes care of the shipping of the goods from one location to another. Similarly, they are shipping the application for the end users using the same concept. Okay, so that's how it originated, and you can get to understand more about the history and evolution in the other video that I'll share again with you if you have not seen it. So coming to the first topic, which is virtualization versus containerization, right? In virtualization, this is how it looks like. You have a physical server, you have a host operating system. See, in certain areas, it is a kind of purpose built operating system for virtualization. They call it as hypervisor. See, in Microsoft world, we install Microsoft Windows Server. On top of it, we enable the Hyper-V feature. Hyper-V is the virtual machine management feature. We call it as hypervisor, and the product name is also Hyper-V in Microsoft. Similarly, VMware, they also have a host operating system which has pre-installed hypervisor capabilities or features. The operating system is purpose built for running multiple virtual machines on the same hardware. So they call it as VMware vSphere. It used to be called as ESXi, ESX, and so on. And we also have two different concepts in virtualization itself. One is the direct bare metal hypervisor, where we directly load the virtualization product directly on the hardware. There is one more concept where you can also load it as an application to run the virtual machine, like VMware Workstation, Oracle Fusion, and so on. But in production environment, they predominantly use the bare metal hypervisor, where you directly install the hypervisor on the physical server, like VMware, vSphere, Microsoft Hyper-V, and so on. So here, you the problem with virtualization earlier, before virtualization, of course, virtualization was a very big success, and it helped IT industry evolve like anything. And without virtualization, cloud might not have happened. Cloud might have been a failure if there was no virtualization. Virtualization, in fact, helped cloud's success. Almost 70% of the success of cloud is because of virtualization. How that happened? If you have that question, see, before virtualization, one physical hardware used to have one application, right? And let's say if there are 100 application, you will have at least two or three environment per application, like UAT, development, testing, pre-prod, production, and so on, right? You might have at least two or three environment per application. people used to, I mean, a company used to have 300 servers for 100 applications, 300 physical servers. And 20 years back, if you think about the specifications, it used to be very small, like 8 GB of memory, 2 CPU, and that was the configuration that was available at that time. So we used to have only hundreds of GB for storage capacity and so on. Now, even a single physical hardware is capable of having petabytes of storage, and you have multiple GBs of I mean, terabytes of memory modules are supported on single hardware. The hardware has evolved like anything. The hardware specifications have improved. And if you are running one application on a very giant hardware with a lot of specification, it's a kind of lot of waste of money there, a lot of waste of resources, in fact. And if you're running only one application on a very big hardware, it's a challenge. And also, if you're running multiple application on the same hardware, to mitigate the usage or optimize the usage, there are quite a lot of challenges, because one application, if they need to restart the OS or restart the hardware, the other applications running on the same hardware will also have to go through the downtime, will also experience the maintenance window, right? To avoid that, what hypervisor did it allowed you to create multiple. I will see if I have a better diagram. um, Traditional virtualization. Yeah. So we used to have we were able to create multiple virtual machines on the same hardware on top of the VMware vSphere or Microsoft Hyper-V, where there are quite a lot of additional benefits also. We can run multiple different versions of operating system. The hypervisor has a kind of Linux-like operating system, but still you are able to run a Windows virtual machine, and we used to run a different flavors of Linux operating system as a VM on the same physical hardware. We can run a minimum of 10 to maximum of even 50, 40, 60 based on the physical hardware configuration. We can run multiple virtual machines. So now, instead of having 300 physical server, what we need in reality after virtualization, the complete physical server environment drastically reduced. Instead of 300 physical servers, let's say assuming that we have only 10 VMs on each physical hardware, we really need only 30 physical servers. Instead of 300 physical servers, we just need only 30 physical servers. And 30 physical servers, in the sense, see, it's not just about physical hardware alone, right? It has reduced the other footprint also. 30 physical server need only 4 to 5 rack, whereas 300 physical servers, it needs quite a lot of racks based on the capacity requirement. It needs at least hundreds of, or I mean at least 50 plus racks were needed to have all those hardware, right? And in turn, there is a quite a lot of power consumption, there is a quite a lot of cooling needed for your data center, because 300 servers emitting heat and needing the cooling capacity, it is going to be huge. Electricity as well as quite a lot of expenses are also there. So maintaining 300 hardware, you need at least 10 different people to maintain those hardware, do the firmware upgrade, do the maintenance, replacement, any fixes in the data center. Also, they need a quite a lot of networking cabling. I mean, 50 rack means 50 network switches are needed, and of course, cabling to storage and other things are involved. So the virtualization definitely helped hardware abstraction. When you say hardware abstraction, it has completely reduced the hardware in the data center almost one tenth, or I mean, it's like we used to have 300 server hardware, and it has reduced to just 30, right? So you can see how much drastical reduction has happened on the physical data center footprint. So hardware abstraction was really helpful for the cloud. And instead of having a very big real estate space for hosting a data center, because of virtualization, we need just a space to have only 4 to 5 racks instead of having 50 or 100 racks, right? So data center size has shrinked, and the people who are needed to maintain the physical data center has also reduced. And in fact, that became the concept of having the hosted cloud platforms like Microsoft and Google, Amazon. They started having a centralized data center for multiple companies because of virtualization. Without virtualization, if you think for each company, they might have needed at least 50 racks, and think about hundreds of customer, they might need a complete city size to host the entire customer into one data center. So that might not be feasible, right? So because of virtualization, the complete data center footprint shrinked. The hardware abstraction is what we call it as virtualization. Okay, coming back here, see for each there was one more challenge, right? See, the clearly there is a hardware abstraction. Clearly data center size has shrunk, but considering the remote support, right? So remotely people have to log into the system, manage and maintain the application. They need to take care of the OS level patching and all those things. So it is clear that instead of 300 host operating system, we have only 30 host operating system. That is reduced. Okay, that is for sure. And the on-premises team in the data center definitely needed is reduced. But here comes the challenge on the VM. Each and every virtual machine has its own operating system, its own guest operating system. So here, so for each of your VM, you have a separate operating system like Windows or Ubuntu or Fedora or Red Hat or whatever, right? So it used to have its own operating system. So we need people to manage those virtual machine operating system remotely. So instead of 300 physical server, it has become 300 virtual machine. So there was no change in the number of guest operating system that is needed to run your application. So 300 physical operating system has become 300 virtual operating system. And in fact, coming to the count of the operating system, the number of operating system has increased because there is 30 more hypervisors to manage. So it is in net it is 330 operating systems to manage. And so that's where people were kind of concerned that they need some other solution to kind of eradicate the number of operating systems, the maintenance, because for each and every application, the guest operating system has to boot, and the guest operating system itself has its own full kernel. So which means for your operating system, if it is Windows, you need to have for OS alone 100 GB. Think about 300 virtual machines consuming 100 GB each. For that itself, you need a plenty of storage just for the operating system. And on top of that, for each and every operating system, it will consume its own CPU, its own memory, its own graphics, and all those things. So each and every single physical hardware used to provide quite a lot of resources in the form of CPU, memory, and hard disk for each and every guest operating system alone. And on top of that, we used to have the applications, we used to have the usage from the application. Okay, so that is another one more layer. But definitely, virtualization helped evolve the IT environment, the data center environment, especially the hardware abstraction really helped customers, the cloud evolution, and all those things. On the other side, it also had very good isolation because each and every application gets its own kernel, its own guest OS login. I mean, it has its own segregation and all those things. So resource sharing is also very much controlled, and there are quite a lot of additional benefits also. Okay, so I already explained about this. I will just come back to here and then summarize again. So this is a different topic which I started with. And containers is where you get OS abstraction, OS level isolation. So instead of having separate operating system for each and every virtual machine in virtualization, Docker container or similar concepts like Podman or libc or those platforms, it doesn't need separate operating system for each and every application. So what it can do is it can share the kernel from the host operating system, and whatever is needed for the application to run, the runtime, the libraries, the dependencies, those will be packaged along with the application, along with the application code, and it will run in an isolated platform. So here the container engine is what has replaced the hypervisor. Instead of VMware vSphere or Microsoft Hyper-V, we have Docker, Podman, and other similar tools to run the container engine here, right? So the trade-off is here we are reducing the 300 operating systems, the guest operating systems is now no more needed. Instead of 30 hypervisor, we are having 30 host operating system with shared kernel, and it can run multiple applications as a container. So there is no separate guest operating system. There is no delay in the booting. There is no resource wastage. So only the application consumption is what is needed for the from the hardware. Only what is needed for your application is what will be consumed in the form of CPU, memory, and so on. So the 300 guest operating system usage is all completely eradicated, and OS level abstraction is what we call it as containerization. Virtualization is hardware level abstraction. It reduced the hardware. Containerization, it reduced the number of guest operating system, right? So here, this is, I hope this is clear. So we are sharing the, in an operating system, there are two layers. One is the kernel layer and the other one is the user layer, which is the utilities, application, and the tools, libraries, all those things. It runs on the user layer, and that is what we generally kind of use it for your application. And that application developer started adding those user layer into the container package itself. So there is nothing really needed on the underlying physical hardware, but you get privacy. Definitely your processes run separately, your file system runs separately. You will start seeing it while you see the containers deployment, and even in the ECS also you will start to see how they are getting segregated, and they can also get its own network, into its own IP address, its own host name. You can also set the limits for your application containers in the form of CPU, memory, and IO limits you can set. So containers are super fast because there is no guest operating system to boot. It boots in few milliseconds, and only it needs few megabytes of memory, not gigabytes, right? And they have a compatible kernel. That is the important thing. I'll come to that clarification later, because people will have confusion whether I can run Windows container on Linux kernel, whether the other way around, right? So there is a question there. I will explain and I'll answer how that works. But generally, at a very high level, yes, Linux container images needs Linux kernel, otherwise it won't work. And see, in Windows also, you have subsystem for Linux, Windows subsystem for Linux, WSL. So you can install it and you can also run Linux containers. But I will explain that little later. So at a very high level, hope this is clear. Can one of you confirm if you're able to follow me and you are able to understand what is virtualization and what is containerization? Or any questions from any of you?
Yes, sir. Virtualization is to reduce the hardware, and containerization is which helps to reduce the operating system workloads.
Yeah, that is correct. But line is breaking for me. Is it for, is my line is also breaking, or it's his side?
Looks like it's for all Stan.
Okay, so my line is clear, right? My line is
Yes, yes, yours is clear.
It's clear to
When
understand.
Sasi speaks, it's
fine, fine. Sasi's line is bad. Okay, that's fine. That's fine. Okay. But I think he understood it. So virtualization is reducing hardware. Containerization is reducing OS. See, that is the basic fundamental differentiation. But on top of that, there are quite a lot of other things, right? Like other benefits. Nowadays, see, you cannot make all your application run on containers. So there is a complete re-platforming, re-architecting. You need application developers to develop your application in the form of microservices or container hosted platform. So definitely your legacy application might have quite a lot of challenge, right? It's not that every single application will run on container. There will be evolution. You have to enhance, you have to do investment for the application code changes and so on. So currently, most of the web application, the CI/CD platform like your Jenkins or Argo CD or any continuous integration, continuous deployment related tools, and even microservices, all of them are running on containers. I think I had a slide. Yeah. So see, a lot of modern companies, right? See, these companies, you might not have heard about these names 25 years back. So these are all modern companies, some of them, right? Not all of them. Definitely, there are some companies which are old enough, like Adobe and all. It's there for some time. But then these are companies which has come into the market in the last 20-25 years. So they started creating their application when virtualization was there, and even when some level of containerization was there. So they started their application in the modern era. So for them, almost all the application that they have developed or running as a microservice or running as a container. So these are the common use cases, right? You can use it for web application, you can use it for backend APIs, you can use it for microservices for many of your application. Complete Amazon, Flipkart, Netflix, they all use microservices to run each and every subcomponent of their application. And similarly, you can run your Jenkins or Argo CD or different tooling on the containerized platform. Even um, almost, I would say 80% of the CI/CD DevOps tools are runs on container only. Okay, and of course you have option to run ECS, ACS, and different tooling on the cloud. Okay, so I think where exactly I had that. Yeah, so there are quite a lot of products that are still running, including Cloud Run from GCP, and the artifact registry is again Docker based. And there are quite a lot of technologies still used in the market. Okay, so any other points? Yeah, see, currently, if you are talking about virtual machine, I already clearly explained on each and every hardware. If operating system itself needs separate OS, disk, CPU, memory, and all those things, you can run only 10 virtual machine on the single hardware. But whereas on the same hardware, you can run hundreds of containers because it doesn't need separate guest OS, separate specifications for them. And also the booting time is very quick for the container because it doesn't have any separate guest OS as such. It's just the runtime stack that has to start, and the application will start running. Typically, it needs few MBs of capacity, whereas you need 100 GB for Linux and Windows, and at least 50 to 60 GB for your Linux operating system alone. On top of that, you need to add the application data and other log and other things. For that, you need additional hard disk capacity. So here the process is completely isolated. The host kernel is what is being shared, not the user space. User space is separate for each and every container. So the application developers will take care of attaching the dependencies, libraries, and other runtime stack that is needed for the application into that. And it is best suited for the modern application. Okay, so this is the evolution. We used to have bare metal server where we used to run one operating system and multiple application on the same operating system. But if you bring down this one single physical server or one operating system, multiple application will be impacted. So that was the challenge 25 years back or 20 years back at least. And after virtualization came in, so we can run multiple VMs for each and every application. It also enabled privacy, as well as it gave the option to kind of do the maintenance and do have separate operating systems, multiple different flavors, multiple different versions of operating system on the same hardware. We used to have Mac, Linux, Windows, and also within Linux also we used to have Ubuntu or Fedora or Red Hat or whatever, right? So we can have multiple flavors, multiple editions, and also we were able to run both 32-bit VMs as well as 64-bit operating system VMs also on the same hardware. Even though the hardware is 64-bit hardware, it supported 32-bit guest operating system. So for backward compatibility also, virtualization was very helpful. And containerization came in. It removed the guest OS that is needed for each and every application, and instead of having separate guest OS, only the user space, only the runtime environment, libraries, dependencies got added into the package, and it started running the containers. So the guest operating system got eliminated, and now completely it's a combination of virtualization and containerization. So the underlying base hardware is having virtualization. On top of the hypervisor, we can also have the container engine. Okay, for we can have one VM running multiple containers for one particular environment or one particular department or one particular customer, and the other virtual machine can completely run a set of containers for a different customer need. So currently, containerization on virtualization is the current combination that you can see in most of the cloud data centers. Okay, so that's the current situation, and you can mix and match also. See, for example, VMware also has its own virtualization tool, as well as it has got its own containerization tool also. So it's like they understand the benefits, they know how it is going to help each other. So containerization on top of virtualization is what is the current situation in almost all the cloud data centers. Okay, so this is a kind of similar aspect, but I'm just showing it in a little bit closer view where how we are running containers on a virtual machine. And these are the four different era of evolution in containerization and virtualization. Okay, so just to conclude, okay, on the virtualization, we used to have the physical infrastructure. On top of that, we used to directly install the vSphere or the Hyper-V and all those things. And on top of that, we used to have the virtual machines with its own separate guest operating system, and we used to run the application earlier in virtualization. These are the common examples: kernel virtual machine, Hyper-V, VMware, vSphere. So these are the top three that was used. And on the container engine, we have Docker, Podman, CRIO, Containerd, and so on. LXC is also one. So this is what are the products that are being used for the containerization enablement. And we used to have only one host operating system sharing the kernel for all the different containerized application. Okay, so before I get into the next topic, one more clarity here. See, application running directly on the physical hardware, right? See, this is the same thing, right? Applications are directly put onto the direct shipping ship, right? What is the challenge we have? And if you properly organize them into a container, what is the benefit? It's the same analogy that we are seeing from the application point of view. So if you are directly installing all the application directly on the server hardware, so people get into a lot of conflict. So people will say my version needs different patch level, different runtime stack, different library file, different OS version. So there will be quite a lot of confusion there, and developers will say it's working in their laptop and it's not working in the system that we are running on the server hardware or on the cloud platform, because there is a difference in the any of the layer. It might be system library difference, or it might be OS version itself might be different, or the patch version might be different. So they will say it's working there, and then after you ship the application code, it might not work on the server hardware or on the cloud platform. So that's where the challenge came in, and the developers completely started shipping their application code along with dependencies, libraries, runtime stack. Everything will be bundled into the container image, and that image itself will have all the necessary libraries, dependencies, and the package that it needs to run the application as a isolated environment. So if this particular application image is being moved to a particular cloud platform or a different data center or a different hardware, it will continue to work, okay, because it is having all the necessary components to run the application within that package itself, within that image and image itself. It will be consistent wherever you are running it, whether you are running it on your own laptop or server hardware or in cloud platform hardware. It will be the same consistent performance wherever you do it. So you just have to develop, deploy, and scale using the Docker engine. I'll show you how to create an image, how to run a container after the image is being created, how to store the images in a secure repository. So all those practical labs we are going to see. So there is no dependency conflict, there is no issues between environment, and you can easily roll back, and you can do easy updates, and it is very portable also. You can move the container image to wherever you want, and it will give the same level of consistent features and benefits for the end users. Okay, so now we are done with the first set of discussion. Second topic was what? Okay, before we get into the Docker architecture, we will talk about a little bit about the Kubernetes, right? See, people have this confusion also. So currently, everyone is talking about Kubernetes. No one is talking about Docker really, because see, Docker has evolved, and Kubernetes is really needed for the containerized environment. See, let's say I have 20 different hardware. Okay, I have 20 different hardware having, let's say, 200 plus containers. And if I want to manage these 20 plus hardware remotely, I need to log into each and every Podman or each Docker system to manage the container running on them. And even if I want to move the container from one particular hardware to other container hardware, I need to take a image, export, import, or backup and restore, or I need to have some kind of downtime. There is no orchestration that is really possible within the platform here. See, Docker has a product called Docker Swarm, which you can use to do the orchestration, automation, movement, and all those things. I'm not talking about Docker Swarm. I'm talking about the Docker server itself, the Docker product here. And that product or the Podman or Containerd, they are product only used for running the container. They are the engine to run the containers on the hardware level. So if you want to move it to another hardware, or if you want to do orchestration, that this container engine doesn't have its own feature. It doesn't have its own functionality to do that. And Docker has developed a product called Docker Swarm, which was useful, but it was not. See, it's the same thing, right? See, companies have um, their own product, and it will work in the cloud platform alone. Let's say Azure has ARM template; it will work. It can be used as the infrastructure code to deploy the Azure resources. But if you talk about Terraform, Terraform can be used for deploying the infrastructure as a code into any platform, right? AWS or Azure or wherever, right? That's what we are going to learn after completing the Docker set of things. We are going to learn Terraform also. See, that's the common product which can be used across the platform. Similarly, Kubernetes can orchestrate the containers across LXC, Containerd, Docker, Podman. It can move container from any hardware to any hardware, any platform to any platform. Like it is compatible with AWS, Azure. It's compatible with your on-premises OpenShift or so. Kubernetes is a centralized orchestration platform or centralized automation platform where it will enable you to move the containers from one hardware to another hardware, do some changes, and if you want to do resource limiting, or if you want to do kind of resource sharing, so all those control plane actions, all those orchestration related stuffs, all those portability and automation and all those things, Kubernetes is the product is going to help you out. So Kubernetes is not a direct replacement of Docker. Instead, Kubernetes started providing you enhanced capabilities in the form of orchestration and automation for the Dockerized environment. So, and why the question here? Did Kubernetes kill Docker? Is it when some people have that doubt, because after Kubernetes, people started only talking about. Let me just little bit zoom in. I think the screen is not that visible. Yeah. So the answer is